Hello and welcome to this quick start video on using LTSpice, where I'm going to go through the basics of using LTSpice, the tools that are available to us, and then we're going to build our first circuit, just a voltage divider, and we'll apply both DC analysis techniques and AC analysis techniques using different sources. So once you've downloaded LTSpice and opened it up, it'll look like you can see on the screen here. Then the first thing we want to do is just simply create a new schematic. So Control N on your keyboard, or you can go into the File menu, and that'll give you a blank canvas, all of which you can drop components onto. In terms of where you're going to find the tools, LTSpice is actually pretty intuitively laid out. So our File menu is just all the standard File, Open, Save, etc. stuff. In our Edit menu, you'll find most of the components, like the common components. You'll find the component library for less common components, things like grounds and everything else, and the ability to move and stretch stuff around too. But all of those things are even more easily accessible through the toolbar here. So you can see just at the toolbar on the top, we've got things like our voltage source easy to drop in, resistor. For more complex components, there's the component library where you can find things like op amps, you can find things like transistors, and you can sort of search for fairly specific components that we might have in the lab. So yeah, all of those kind of circuit drawing tools are easily accessible without having to go into any menus at all. Then the other main tab that contains stuff that's useful to us at the moment is the Simulate tab, and that's going to be where we set up our simulations both for DC, AC, and there's also some other types that we won't get into in this video, but we might in future videos. So yeah, that's pretty much LTSpice's layout. It's pretty nice to use. It's much more beginner friendly than other toolboxes I've used. So what we'll do is we'll dive straight into our first circuit. What I'm going to do as a start is I'm going to build a voltage divider that just has a DC source, and we'll perform analysis on that to see what the different currents and voltages and stuff are. Then after that, we're going to change that source to AC, and we'll go through the process of having a look at what AC analysis would look like. So let's get started. So our voltage source is available there. We can click that one and drop it in. And then right next to it, you can hit escape on your keyboard to stop putting components down. Right next to it is the resistor. You'll also see when you hover over these components that they've got keyboard shortcuts in the brackets. So I don't even need to click it. I can just press R for resistor on my keyboard, and most of them are pretty logical, like C is capacitor, L is inductor. So it's sort of what you might think that component would be named. And if you needed to rotate components, you can also press Control R to do so. In this case, we don't. They can just both be vertical stacked like that. And then we want to connect them together. So to do that, you'd want to use the wire tool, which is available here, or it's just W on your keyboard, and it'll give you little guidelines to help you line everything up as you go around. And that wire tool will stay on until you're done with it. So then we would want to assign some values to all of this. So let's say we just have a 12-volt source, and I'll pick some random values for my resistors. Let's go with 1K, and let's go with 4K, say. So that's all assigned now. Those values are all sorted. The only thing we're missing electrically is our ground. So again, you can click on the button, G for ground is the alternative, and you pop it in and connect a wire up so that it's all connected in. So that's everything we technically need to be able to run an analysis. The other thing that can be helpful though is if you've got actual points of interest. So for example, if we wanted to find the output voltage across R2, then it can be useful to add in node names as well. So the button for doing that is this label net button, or N on your keyboard, and that'll just pop up with a text box where you can give it a name. So let's just call it VO, and we can pop that one there. I could also do one for VIN if I wanted. Why not? Let's do it just so we can practice it. So VI for VIN, and I'll just pop that one above our source there. So that just means when I get to running my analysis, we'll be more easily able to see what those are. So that's the design done, simple circuit. Now we want to actually start our simulation. So you can go simulate run, or you can just click the play on your toolbar there. And it pops up with a whole bunch of different options. So the main ones that we will use will be transient analysis, which does a time series analysis useful for AC signals. DC operating point, which gives us the DC characteristics of a circuit, like the one that we're looking at here. Some other ones that might be useful in specific cases include things like DC sweep, which allow you to change the voltage of its DC source between a start and an end point and see how the different components respond. That's useful in later subjects like electronics, where we might want to characterize more advanced components like diodes and transistors. And then there's also some things around other types of AC analysis, transient frequency, that also might be useful for later subjects too. So starting off, I'm just going to do a DC operating point analysis, which just simply calculates the voltages and currents associated with the circuit that I've drawn. So I click that, there's no other settings to do, I press OK, and it'll place this .op. That's a SPICE directive that tells LTSpice what it is running. And it pops up with our nicely named nodes. So VVI is 12 volts, it means that's 12 volts just up there, which is what we would expect given we put a 12 volt source there. And then the voltage here is 9.6 volts at our output, which makes sense if you do the math as well. Now, in terms of the currents can be a little bit tricky to discern because a quirk of LTSpice is that the resistors actually have a positive and a negative, but they don't explicitly tell you which one is which on the symbol. So really, to figure out which direction this current is going in, the best thing to do is just consider the voltages either side. So the voltage at the top of this resistor is higher than the voltage at the bottom, therefore the current is flowing that way. Same thing with this next one, the voltage at VO is 9.6, at the bottom it's going to be 0, so the current's flowing down as well. So not super intuitive just by looking at it, you kind of have to use the voltages to infer it. If you are finding it difficult though to infer what direction the currents are going in, just, because you've got a complex circuit or whatever else, the other option is you actually can run a transient analysis on a DC circuit. So even though transient analysis is designed for signals that change, like AC signals, it can be used for DC. You'll just get a whole bunch of flat lines, and I'll show you what that looks like. So I'm going to close this off and I'll delete that operating point. And I'm just going to go into my analysis configuration and I'm going to switch over to a transient analysis. Now the start and stop time don't really matter because, like I said, we don't really care about the time series. We're just trying to use it to get a better understanding of where things are going in this particular circuit. So let's just say we want to stop at 0.1 seconds, start at 0 and take a small time step. Doesn't really matter. Pop that down, run our analysis. And what happens is it pops up with this oscilloscope-like display, and we can actually click on different parts of our circuit to figure out what the values are. So our voltages again can be probed. I can click that and see that we've got exactly 12 volts at VI. That's good. I can probe here and see in that awful blue color, let's make that a bit brighter, that one is 9.6 volts. I could also probe down the bottom. No, it's not going to let me because it's 0. So yeah, it knows that it's 0 down there. That's why it's not showing up. And then for my currents, I can do the same thing. So I can hover over and you can see that, like I said just before, this current goes from top to bottom. But I can also click on that or double click if you want that to be the only one visible. Again, it's picked an awful color. I don't know why the blue even exists, to be perfectly honest. And we can see that the current there is 2.4 milliamps. Which we would expect to also be the case for this one, and we can see that it is. So yeah, if you're having trouble inferring the direction, this is nice because it actually shows you the direction that it is assuming. So same with this one, it says that it's assuming this direction, but then it's negative 2.4. So in actual fact, it's going from the negative terminal to the positive terminal. So it just gives you a little bit more insight into how LTSpice is actually interpreting that analysis that you've done. So yeah, that's another option if you're a little bit confused on things like current directions. So that's our DC circuit analysed. That's the process that you will go through for any DC analysis. Doesn't really matter how complex your circuit is. Obviously, the more complex it is, the more helpful it is to make sure you're adding these labels, because without those labels, I'll just show you what it looks like without. Without those labels, if we run a DC operating point analysis, it just kind of gives you these generic names of N001, N002. And you can imagine if you had, 10 nodes or something like that, trying to guess which one it's decided is 1, 2, 3, or 10 is going to be pretty difficult to do. So adding some names will help you out. Great. So now what I'm going to do is I'm going to change this circuit over to having an AC source so that we can have a look at what transient analysis would look like in a more realistic scenario where we actually have a varying signal. So if I right click on my voltage source, it only has two options by default, the DC value and a series resistance where we could simulate a non-ideal source. We can go into the advanced tab though and we get a whole bunch more options. So we get exponential waveforms, pulse waveforms, and the one that I'm going to use today is the sine waveform. And we can set a whole bunch of properties of that. So DC offset is how far it's shifted off the zero centering point. So I don't want to shift it, I'll just make it 0. Amplitude is what's its peak going to be. Let's stick with 12. Frequency can be anything you like. I'm going to say it's 50 Hertz today. And then there's other parameters for like, do you want to delay it? Other like small parameters that you can tweak to get the shape exactly the way you want it. But in most cases, you're going to have a pretty clean sine wave. So the parameters I've set will be the main ones that you want to use. So press OK, and you can see it's updated the information of that there. So I might even just move that off so that it's a bit out of the way. And that's all ready to go. Now with our transient analysis, it's not as important really to label the nodes because we can physically probe it with that little oscilloscope probe tool. So you can not worry about it as much if you're just doing AC. When we go then to set up our simulation, our transient analysis, we might go to 0.1. We've got a pretty low frequency, so that should hopefully give us enough of a view. Start at 0, and then our maximum time step will just be something small. That way we just get a nice smooth waveform. If you make that too big, you'll just kind of get jagged waveforms that might not give you the full picture of what the output should look like. Hit OK, that'll get dropped down there again, and it opens up your little scope again. And you can just start probing the different areas of interest. So we can have a look at what our input looks like. It looks like a 12-volt sinusoidal signal, shocking. And then we can have a look at what our output looks like in comparison. And you can see that that's been reduced a little bit due to the voltage that drops in that top resistor. I guess we could also edit this circuit to make it so that the two resistors are the same, because then we should see that the output will be exactly half. So you can see there that that peaks. Actually, you can't really see because it's that awful blue color again. There's a better color. So you can see that we've got now we've got half of the voltage that we had originally. In this case, the values are sort of clear to read because they exactly are at a whole number interval. But if you wanted to take a closer look at what the values are, you can select whichever trace you're interested in, and it'll add a cursor. And that'll just allow you to drag through, and you can see in this little window down here that it's changing sort of where it's looking at. So yeah, you can do that by clicking on either of them. You can also right click and add additional traces. You can place cursors on the active trace and do a few other things there as well. I guess the other thing I haven't shown yet is that you can also do this for the currents, so you can have a look at the currents that are flowing through these different resistors, and you can see that they're the same because they're in the same pathway, but you can see what their values are as well. So you can place a cursor on that active trace and you can see that it peaks out at 6 milliamps and the trough is -6 milliamps, just like we would expect. So that's transient analysis in a nutshell. That is all the basic skills you need now to get started with simulating and analysing your first circuits. So a really good way to get started is for any questions that you're doing in class and stuff like that, you can actually do a simulation to confirm that the outputs are what you would expect based on your mathematical answer. And you will also be asked to do different simulation exercises in some subjects, or you'll be using simulation to design circuits for pracs and design projects as well. So yeah, these skills will apply to much more complicated circuits than we've covered today. It's the same process that you just are repeating with more elements. Hopefully you found this helpful, and I will see you in future skills videos.